Hi everyone, this is Professor Oakes, and in this section we are going to discuss sketching polar graphs. So here is some information on the symmetry of polar graphs. So for the first one here, if we replace theta by the opposite of theta, or theta by pi minus theta, and r by the opposite of r, then we get an equivalent equation that implies symmetry about the line obtained by extending the polar axis. So as a quick review here, all right, here is the pole, and here is the polar axis, and then this would be at a right angle to the polar axis, the line theta equals pi over 2. All right, so that's just a review of the general setup of what we're talking about here. So for the second scenario here, if we replace theta by pi minus theta, or theta by the opposite of theta, and r by the opposite of r, then the equivalent equation implies symmetry about the line through the pole perpendicular to the polar axis. And this line through the pole perpendicular to the polar axis is the line theta equals pi over 2. All right, so that's why this was important up here. Now, the third scenario is if we replace theta by theta plus pi, or r by the opposite of r, then we have symmetry about the pole. So now, before we go into this a little bit further, let's talk about some of the common polar graphs of the spiral. So if f is either an increasing or decreasing function, then the graph of r equals f of theta will have a spiral shape. So if a is greater than 0, and we have r is a theta for theta greater than or equal to 0, then that's one type of spiral called an Archimedean spiral. Now, I'll say one thing about this. I won't actually draw any of these here that I wouldn't expect you to be able to draw yourself, and so I'm not a very good drawer. So you should expect most of these not to be too complicated. All right, if they were complicated, I would already have the graphs already printed out here. So the Archimedean spiral is a spiral that starts at the pole here and then spirals outward in a counterclockwise direction like this. All right. Now, if a is greater than 0 and r is e to the power of a theta, then we have something called a logarithmic spiral. And here's what this one looks like. All right, so this one actually goes in a clockwise direction, inward toward the inward toward the pole, depending on which direction you are following the spiral here. All right, let's look at another common polar graph, the cardioid. So if A is greater than 0 and R is equal to A times 1 plus or minus cosine of theta, or R is equal to A times 1 plus or minus the sine of theta, then you will have a cardioid. So let's just do one example here. R is A times 1 plus sine of theta. Then this particular cardioid would look like this. All right, so you can probably see why it might be called a cardioid, and that's what a cardioid of the form A times 1 plus sine of theta would look like. All right, a limaçon. All right, so if A is greater than 0 and if B is greater than 0, R equals A plus or minus B cosine of theta, or R equals A plus or minus B sine of theta. Theta is a limaçon. So if A is between 0 and B, then this is what the graph will look like. All right, so it looks like this. And if 0 is less than A over 2, less than B, less than A, then what do you have here? You have something that looks like this. All right. So if A is equal to B, then this is a cardioid. And I hope that you can see that, because if you distribute this A here for the cardioid, you would have A plus or minus A cosine of theta, or this A plus or minus A sine of theta. So if A was equal to B, then if these were both the same, then you would have a cardioid instead of a limaçon. All right. And if you have 0 less than B less than or equal to A over 2, then here's what the graph looks like. And it's really just, in other words, it's a puddle of mud or whatever you want to call it. In other words, called a distorted circle. All right, very good. Now, a leminscate, if A is greater than 0 and R squared is A squared sine of 2 theta, or R squared is A squared cosine of 2 theta, you'll get a leminscate. And a leminscate is just what most people would probably call an infinity sign or something to that effect. Now, for an n-leaved rows, all right? So if you have R is A sine of K theta, or R is A cosine of K theta, where the number of leaves of the rows, n, all right, is K, if K is odd, and 2K if K is even. So here is an example of a 4-leaved rows. All right, again, this is just an example, but you could draw any number of leaves on here. You just have to have the proper equation for it. And here we go. This is a 4-leaved rows example. So, how do you know the direction of a polar graph? Well, consider a polar curve, r equals f of theta, where f is a differentiable function of theta, and let L denote the tangent line to the curve at the polar point P equals R theta. Let alpha be the angle measured from the polar axis to the tangent line L. And thus, since the polar axis coincides with the x-axis, the slope of the line in the Cartesian system is tangent of alpha is dr d theta sine theta plus r cosine of theta all over dr d theta cosine theta minus r sine of theta. Now, if a polar curve passes through the pole for a particular value of theta, the tangent line to the curve at the pole has a slope equal to tangent of theta, and furthermore, tangent of psi is, that's a new symbol here, but this is the angle measured from the radial line through P to the tangent line L. All right, so this is R over dr d theta. So let's do some examples of testing for symmetry and then finding the slope of the line here in the Cartesian system here. So test for symmetry. R sine of theta equals 5 with respect to the polar axis. So remember, for testing symmetry with respect to the polar axis, we can replace theta by the opposite of theta, or theta by pi minus theta, and r by the opposite of r. So let's just do the first option, where we are going to just replace theta by the opposite of theta. So let's see, we have r sine of theta equals 5, but if we replace theta by the opposite of theta, we have r sine of the opposite of theta is 5. And then the sine of the opposite of theta is the opposite of sine of theta, which is equal to 5. And so that's the opposite of r sine of theta is 5. And you are trying to check to see if what you had before and after you replace theta by the opposite of theta are the same. But these are not equivalent. So that means that, therefore, r sine of theta equals 5 is not symmetric with respect to, the polar axis. All right, so by the way, one thing that you should remember or try to remember is all of the trigonometric identities that you've ever learned in your entire life. And so one of them I used right here, and that was that the sine of the opposite of theta is the opposite of the sine of theta. And then you might find this one helpful once in a while. Cosine of the opposite of theta is the cosine of theta. All right, so try to remember every trigonometric identity you've ever learned in your entire life. That would definitely help you here. Now, let's test the polar equation r sine of theta equals 5, the same one, for symmetry with respect to the line theta equals pi over 2. And remember, there are two ways that we could test for this symmetry, and it is by replacing theta by pi minus theta, or theta by the opposite of theta and r by the opposite of r. So let's go with the second option here. It doesn't matter which one, but here we're going to just replace the theta by the opposite of theta and r by the opposite of r. So instead of r sine of theta equals 5, we have the opposite of r sine of the opposite of theta equals 5. And remember that the sine of the opposite of theta was the opposite of the sine of theta. So we have the opposite of r, opposite of sine of theta equals 5. And that ends up, when we multiply this together, being r sine of theta equals 5. These two are equivalent, what we had before and after we did the substitutions. So therefore, r sine of theta equals 5 is symmetric with respect to the line theta equals pi over 2. All right, so let's do this one more time here with respect to the pole. And remember, for symmetry with respect to the pole, we can replace theta by pi plus theta, or theta plus pi, or r by the opposite of r. So you can pick whichever one is easier, or whichever one you actually remember. So let's replace the r by the opposite of r here. So if we start it with r, sine of theta is equal to 5, and now we have the opposite of r, sine of theta is equal to 5, we see that these are not equivalent, and therefore the r sine of theta equals 5 is not symmetric with respect to the pole. All right, now let's sketch a graph of the equation then. So r sine of theta is 5, but r sine of theta is y, so we have y equals 5. So this will be a line here, and here is theta equals pi over 2. And remember, I did know that this was symmetric with respect to the line theta equals pi over 2, but since this is just a horizontal line at 5, this is what this looks like. All right, maybe I should have gotten my ruler. What a time to be alive. All right, so I'll get my ruler here. I don't know if that's much better, but here we go. What a time to be alive. So there you go. All right, so again, here is the pole. Right, here is the polar axis, and then you can see here that this is definitely symmetric with respect to the line pi over 2. All right. Now, let's look at another great example here. R equals 2. Is there symmetry with respect to the polar axis? Well, we can replace theta by the opposite of theta. So r equals 2 is still r equals 2. So yes, there's symmetry with respect to the polar axis. Is there symmetry with respect to the line pi over 2, or theta equals pi over 2? Well, let's replace theta by pi minus theta. Well, r equals 2 is still r equals 2, so yes. And is there symmetry with respect to the pole? Well, let's replace the theta by theta plus pi. Well, r equals 2 is still r equals 2. So this r equals 2 is symmetric with respect to the polar axis, the line theta equals pi over 2, and to the pole. Now let's sketch the graph of the equation. So this is a r equals 2. If we know what this is actually a circle. All right, remember that this is a circle with radius of let's see, 2. All right. So again, if you didn't remember this, you could square each side to get r squared is 4, but r squared is x squared plus y squared, so x squared plus y squared is 4. All right, so it's a circle with radius of 2 and a center at the pole, all right, at 0, 0. So here, and radius 2. Here we go. All right, now, if you're wondering about the different ways to show the symmetries, and if you happen to replace, say, r by the opposite of r instead of theta by theta plus pi, just remember that r equals 2 and r equals -2 have the same graph. So these two actually are equivalent, and are equivalent. So just remember that in case you may have went and tried this a different method, or you tried the problem on your own and got r equals -2 and you thought that it wasn't equivalent. It actually is equivalent, because by equivalency, again, we can look at the graph to check that in this case. All right, so now let's look at another wonderful and great example here. Find the slope of the tangent line to the graph of r equals secant squared theta at the point 4 pi over 3. All right, so we know that the slope of the tangent line is tangent of alpha, so that was dr d theta sine theta plus r cosine of theta all over dr d theta cosine of theta minus r sine of theta. Hopefully you have that memorized already, and everything else that I've mentioned that you should memorize here. So let's figure out what dr d theta is first. So if r is secant squared theta, dr d theta is 2 secant of theta times secant theta tangent of theta. Now we substitute this in here. So what do we have? We have 2 secant theta, tangent theta, sine theta, plus r cosine of theta, all over 2 secant theta, tangent theta, cosine theta, minus r sine of theta. Now, you could go ahead and simplify this if you felt like it would help you simplify the process here once you went ahead and substituted the r and the theta, but you don't necessarily have to simplify this, all right? So if I just substituted the r and the theta directly, I have 2 secant of, secant of pi over 3, secant of pi over 3, tangent of pi over 3, sine of pi over 3, plus r was 4, so 4 cosine of pi over 3, all over 2 secant of pi over 3, secant of pi over 3, tangent of pi over 3, cosine of pi over 3, minus 4 sine of pi over 3, and the secant of pi over 3, well, that is going to be 2. So we have, well, let's see, what do we have? We have, I hope I have room for all of this, but maybe I will, hopefully. All right, so 2 times 2 times 2. The tangent of pi over 3 is the square root of 3. The sine of pi over 3 is square root of 3 over 2. And then the cosine of pi over 3 is a half all over 2. Secant pi over 3, 2. Secant pi over 3, 2. Tangent of pi over 3, square root of 3. Cosine of pi over 3, a half. Minus 4, sine of pi over 3, square root of 3 over 2. And then go ahead and simplify all of this. So here, it looks like I can divide out a 2, divide out a 2, and then we have 2 times root 3 times root 3, that 2 times 3, that ends up being 12, and 4 times a half is 2, so 12 plus 2. Then we have, let's see, 2 times root 3, that's 4 root 3, and minus 4 times root 3 over 2, 4 over 2, or 4 divided by 2 is 2, so minus 2 root 3, so this is 14 over 2 root 3, or 7 over root 3. What a time to be alive. So that is the slope of the tangent line to the graph of r equals secant squared theta at the point 4 pi over 3. All right, let's do this last example here. Find the tangent of psi on the graph of r squared equals cosecant of 2 theta. There probably should be parentheses around there. At the point 1 pi over 4. So remember, the tangent of psi was r over dr d theta. All right, so we need dr d theta. So 2r dr d theta. Remember to use implicit differentiation here. All right, that will be equal to negative 2 cosecant of 2 theta cotangent of 2 theta. And now I'll divide by the 2r, so dr d theta is negative 2 cosecant of 2 theta cotangent of 2 theta over 2r. And the 2's divide out, so then we have dr d theta is negative cosecant 2 theta cotangent 2 theta over r. Now, I'll substitute this in over here. So we have r over negative cosecant 2 theta cotangent 2 theta over r. We'll multiply by the reciprocal here. So what do we have? R times the r over negative cosecant 2 theta cotangent 2 theta. And now at the point 1 pi over 4 r theta, we have at 1 pi over 4, we have 1 times 1 over negative cosecant of 2 times pi over 4 times cotangent of 2 times pi over 4. And that will be 1 over, 0, which means this is undefined. What a time to be alive. I really hope that you enjoyed this video and that you have time to memorize everything that I mentioned that you should memorize, and that you are already looking forward to the next video. What a time to be alive. I hope that you have a great day.